Hey, future doctors. I know I mentioned I would show you how to do the sliding block sort of problem without breaking things down into vectors at all. So I wanted to give you a little demonstration of that with one of my little bonus videos right now. So I hope you enjoy. So the first thing I'm going to do is draw a ramp. Maybe I'll draw it kind of, maybe a big ramp. So here's the floor that the ramp is sitting on. Here's the angle of the incline. So this would be a short angle. This would be a larger angle. This would be a 90-degree angle. This would be like 45, 60, 30, 0. So here's my, my inclined plane or my ramp. And here's a third line I'll draw just to make it like an actual like skateboard ramp. And we could always draw that line. Note that this is a 90-degree angle here between the vertical line and the ground. And there's some kind of angle, just like we said, of incline. This we could call theta. And the next thing I'll do is I'll put a block on this ramp. I'll give it maybe like a different color, like a red block. Yeah, red's good. Here it is. And we can call this M1, like mass number 1. Here we go. M1 is that block. And we want to be able to draw our force vectors in this situation easily. So the first one we should always think about, I would say, is gravity right away. And gravity should point straight down towards the center of the Earth. It doesn't matter that we're on this angled inclined plane. Gravity is still going to point straight down no matter what, because that's what gravity does to masses. It pulls them towards other masses, in this case, the center of the Earth. So here we can call this like f of g here. And then the other force vector I want to be able to draw here is that of the normal force, which is due to the blocks squishing against the ramp, so to speak. They're squishing against each other. And so the block's going to push on the ramp, and then the ramp is going to push back on the block upward like this. So there's the two forces. I'm just ignoring maybe friction or anything like that, anything like friction at this point. So now normally you might see people say, okay, you should turn the forces now, or you should break them down into x's and y's and things like that. I don't do that. What I do if I'm trying to derive the downward force that this block is experiencing on the ramp is I just use the head to tail, vector addition method. So I can either grab my f of n and sort of add it to the green vector here, or if I wanted to, I could grab my green vector, my f of g, and add it to the magenta, to the f of n vector. Now you can see I didn't draw these lines perfectly, but if we were drawing them proportionally, what it should look like is this magenta vector here, my f of n, should look just about like that. Okay. And when you add vectors head to tail, the next line we'll draw is connecting these two. So I'll draw my resultant vector. What color should I use? Maybe blue. And this is the force down the ramp right here. That arrow's a little too big. This is the net force of this block down the ramp. And you know that this block is going to slide down the ramp, so this must be what the net force looks like. It must be pointing down the ramp, because that's how blocks slide on ramps. And so I'm going to just move this f of n label here, f of n, and I'll say here, this blue line, we'll call that f. I'm going to call it f down, like f down the ramp. And what's interesting here is if I start to remove, let's say if I remove the block, we can see how the whole f of g sine theta and f of g cosine theta are derived. Let's see if I can remove the block here. Yes. Okay. I'm really lucky. There we go. I'm removing the block just so you can see the vector arrows by themselves. And you might kind of notice some things here. First of all, that you could prove, if you wanted to, that this angle right here is in fact this angle right here. just like this 90 degree over here, this 90 degree angle over here is in fact a little 90 degree angle right here. And if I were to draw another angle here just for fun, 1, 2, this would in fact be the same as this angle right here. You could kind of like prove that with trigonometry if you wanted. You could say like, okay, this angle is the same as this angle, and this angle is the same as this angle. You could definitely prove this, but it'll get a little bit crowded to do that, and I'd have to kind of extend these vectors, but this is just a fact you can memorize, or if you want, you can prove it to yourself. But basically, the little triangle we just made with the 3 colored lines is the same triangle as the ramp itself. And this way, we don't have to break anything down into components or anything. I can just actually kind of delete my ramp if I want. Maybe I'll just kind of keep this angle right here to remind us that this is our angle theta. And I'll say, let's get rid of this one. And if we look at this triangle, this is a right triangle. So I can say, okay, sine of theta is equal to, opposite over hypotenuse. Well, in this case, opposite is the blue line. So I could write it like that. Sine theta is equal to the blue line divided by the hypotenuse, which is the green line. If you look at this triangle, you kind of just tilt your head a little bit, you can see this is the hypotenuse. But those lines, we can see they're labeled. So I can say, okay, sine theta is equal to the f, down the ramp due to these 2 vectors, divided by the hypotenuse, which is f of g. And as a result, I can solve for f down. I can say f of g sine theta is equal to the force down the ramp, that net force down the ramp. And we can just see this based on the fact that this is a right triangle. We're just using our basic trigonometry here. We haven't broken anything down into components or anything like that. But the fact that this little triangle, the angle right here of this little triangle, is the same as this angle on our original inclined plane, means that these relationships are true. And then the other one would be the f of n right here. What could we do about that? Well, going back to trigonometry, we know cosine theta is adjacent over hypotenuse. So we could do the same sort of thing for f of n. We could say cosine theta equals adjacent divided by hypotenuse. So therefore, cosine theta is equal to the magenta divided by the green line in this drawing. And therefore, cosine theta is equal to what the magenta is, which is f of n, divided by what the green line is, which is f of g. And so we can say, okay, f of g cosine theta equals f of n. And there you got it. I mean, that's all there is to it. We just derived the fact that f of g sine theta is that sort of net force down the ramp, and f of g cosine theta is the normal force. Now, I called this the net force because this is a frictionless universe in my little hypothetical right now. If there were other forces like friction, you would need to account for those to get the net. But f of g sine theta, that's this blue vector down the ramp due to f of g and f of n. And f of g cosine theta, that's going to solve for f of n. And remember, theta is just your angle of incline on your original plane. And there's your proof.